Okay, so today we're diving into a story that could literally rewrite the textbooks. We're talking about a mathematical wall, one that's been standing for 200 years, and someone is claiming they've just completely smashed through it.
So let me just start with this question for you. What if a proven mathematical impossibility just wasn't? What if something that everyone, and I mean everyone in the math world agreed couldn't be done, actually could?
Now, to really get your head around how massive this claim is, we've got to rewind a bit. We need to look at the problem itself, this wall in the world of algebra that's been setting the rules for centuries.
For ages, mathematicians have been on this quest, right? They've been hunting for a kind of master key, a single universal formula that could crack open any polynomial equation you throw at it, no matter how ridiculously complex it gets.
And for a long time, it looked like we were making great progress. I mean, look at this. Way back in ancient times, we figured out second-degree equations, quadratics. Then, fast forward to the 16th century, and boom, we cracked degrees 3 and 4. Things were looking good. And then, it all just stopped. A complete dead end. In 1824, this theorem drops and basically says, all right, everyone, pack it up, end of the line.
And that theorem is Abel's impossibility theorem. For 200 years, this has been gospel. Now, the crucial thing to get here is that it didn't just say, hey, we haven't found a solution yet. No, it said a solution can't be found, not with the tools we have anyway. It wasn't a puzzle just waiting for a clever mind. It was a proven, certified, stamped impossibility. Or so we all thought.
But then, after 2 centuries of mathematical silence on this front, a challenger steps into the ring, and they're making an absolutely extraordinary claim.
And that challenger's name is Professor Mourad Sultan Ezouidi. He's an internationally recognized mathematician, and he's come forward with a brand new method that doesn't just question this 200-year-old law, it goes right up and challenges it head on.
And yeah, he is not shy about it. This quote from him says it all. Abel's theorem is not the final word, but a milestone now surpassed. He's basically saying, look, Abel wasn't wrong, he just didn't see the whole picture. It was a big step, for sure, but it's a step we've now gone past.
So what's he proposing instead? It's called Ezouidi's theorem, and it claims to do the very thing everyone said was impossible, find exact symbolic solutions. And when I say symbolic, I mean a perfect, clean answer written with symbols, not some messy, endless decimal number that's just an approximation. And he's saying this works for equations of the 20th degree, and even higher. It's wild.
So what we have here is this incredible clash. It's not just one formula versus another. We're talking about 2 totally different philosophies, 2 competing ideas about what's even possible in the world of math.
Okay, so on one side, you've got the old school, the classical view. This is the world shaped by Abel's theorem. It basically says, hey, some problems just have limits, they're unsolvable, that's just the way it is. But then you have Ezouidi's view. He calls that way of thinking fatalism. He's convinced that an exact answer always exists, hidden somewhere. We just haven't had the right tools to dig it.
When you boil it all down, the real fight here is about accuracy. For anything tougher than a 4th-degree equation, classical methods pretty much have to give up and use numerical estimates. Answers that are close, but they're not perfect. Ezouidi's theorem, on the other hand, claims to deliver 100% exact, algebraically perfect answers every single time. That's not just an improvement, that's a whole new ballgame.
So you might be asking, why did the old methods fail in the first place? Well, it really came down to the tools they were using. The whole approach was built around things like square roots and cube roots. But once you get to equations of the 5th degree and higher, the complexity just explodes. It's like trying to build a skyscraper with a hammer and a screwdriver. The tools just aren't up to the job. You're forced to abandon the search for a perfect answer and just settle for close enough. Okay, so how does this new method supposedly pull off this magic trick? Let's actually take a look at how it breaks down one of these unsolvable equations.
All right, here it is. The final boss. A 20th degree polynomial. Just looking at it, you can see why for 200 years people said, nope, can't be done. The complexity is just absolutely staggering.
The secret sauce here is a concept called recursion. The best way to think about it is like a set of Russian nesting dolls. Instead of trying to smash the whole thing open at once, the method cleverly finds the first, outermost piece of the answer. Then it uses that piece to find the next one inside, and that one to find the next, and so on. It builds this perfect, unbreakable chain of logic step by step.
So the process kicks off with the very first calculation. It finds the value for k equals 1. This is the first domino to fall. And remember, every single step here is perfectly symbolic. No fuzzy math, no estimates allowed.
And from there, it just builds on itself. The answer from step 1 becomes the key to unlocking step 2, and the answer from step 2 unlocks step 3. It's this beautiful cascade where each new piece is derived with perfect precision from the one before it. Zero guesswork, zero approximation.
Now just picture this process continuing. K equals 4, K equals 5, 6, 7. It just keeps going all the way up to 19. And with each and every step, another exact piece of the puzzle falls into place until finally, all 20 symbolic roots of the equation are revealed.
So, what's the big picture here? What does all this actually mean? Well, if this claim is for real, if it holds up to scrutiny, it's not just about solving one tough equation. This could fundamentally rewrite the rules of algebra as we know them.
I think this quote says it perfectly. Limits exist only until they are surpassed. It really gets to the heart of it, right? It reframes these mathematical limits not as impossible walls, but just as frontiers that were waiting for someone to come along with a new map.
And the implications, they're huge. We're talking about the possibility of a universal formula for all polynomial degrees, the end of having to settle for close enough answers, and of course, the complete shattering of a mathematical boundary that's been in place for 2 centuries.
So in the end, this discovery is about more than just solving an equation. It's really about redefining what it even means to solve something. It's a potential shift away from the world of good enough approximations and back to the ideal of a perfectly, verifiably exact answer.
And that just leaves us with this one big, fascinating question to chew on. If a mathematical truth that's been accepted for 200 years can be completely rewritten, what other so-called limits in science and math are out there, just waiting for someone to come along and break right through them?